All right, what we're going to be talking about today is linear programming, and we're just going to be getting into it. This is going to be a two-day assignment, a two-day topic, because there's a lot that goes into linear programming. So today is just going to be an introduction. It's going to be a little bit different style of a video, but hopefully you'll be able to follow along. Homework assignment is really just 6 problems, and we're only doing the last part of linear programming. But let me give you an idea of what linear programming is. It's a powerful tool that can allow us to save a lot of money, do a lot of things a lot more effectively and efficiently than without knowing linear programming. So let's take a look at this first example here. And I'm kind of showing you all this at the beginning. What we're looking to do here is trying to find a way to maximize an objective. So if I'm reading this is our main statement right here. It says the values of x and y that maximize this profit function. And so we could assume that we're trying to find the most profit that we can make. And so we decide that there is a function, and we could describe the profit with a particular function. In this case, the profit is 3 times whatever x is plus 2 times whatever y is. But a lot of times we have some what are called constraints, and constraints are simply limitations on what we have as far as our profit. A lot of times our profit is limited on what we can sell. If you let's say you have a t-shirt making company and you sell, you make $5 with every t-shirt that you sell. Well, you can't sell 1 million t-shirts because you're limited on the people who will buy your t-shirts. You also might be limited on the amount of t-shirts that you can make. And so there's some constraints, and those are what the constraints are. And so this really doesn't have a context with it. This problem doesn't, but we can take a look at the constraints here. They are defined by inequalities, which we went over in assignment number 4. And those constraints are graphed to create what is called a feasible region. And so if I were to graph these 4 inequalities, here's the first one, y equals 3/2 x minus 3. That's this line here. Started at -3, which would have been down here, which is off the screen a little bit. And the slope is 3/2, so I would go up 3 and over 2. And if I were to graph that, it would be a solid line, and I would shade above it. Then when I graph the second equation, it starts at 7. The y-intercept is at 7, which we can see right here. The slope is -1, so it goes downhill. It's a solid line. And we would shade below it. And then we also have 2 equations here that x is greater than or equal to 0. And so we're only talking about the x values that are greater than 0, like 1 and 2 and 3. And y is also greater than 0. So the y values are greater than 0. So we're above the x-axis. And so if we were to graph all of those inequalities and then shade the appropriate area, what we would get is this area in here, which we're going to refer to as the feasible region. That's the feasible area that makes sense with what our constraints tell us we can do. That would limit us from producing like 1 million t-shirts so that we can make $5 million in profit or whatever. And so we're going to talk more about the constraints later on, but right now what you need to know is that you're going to take the constraints and graph those constraints and come up with what is called a feasible region. And then within that feasible region, all of these points in the feasible region are production levels that you can produce 1 x and 1 y. You can produce 2 x's and 2 y's, and that would be here. But what we want to do is plug all those points in so that we get a maximum value for our profit. Well, there's 1 million points in here. There's an infinite number of points in here. The maximum number and the minimum number is going to be the vertices of that feasible region. And so the vertices are like the corners. So it could be this point, which is labeled D. It could be this point, which is labeled C. It could be this point B, which is at the point 2, 0. And it could be the point A, which is labeled 0, 0. And so step 2 would be identifying what those vertices are. And so in this particular case, we have 4 vertices. So we really wouldn't need to test an infinite number of points to see what gives us the maximum value for this feasible region. We would just have to test these 4 points. And when I say test those 4 points, essentially what you're going to be doing is you're going to be plugging in the x value and the y value into our objective function. And again, our objective is to maximize the profit. So what I'm going to do for point A is plug in the x and the y value. The x is 0 and the y is 0. And if I plug the x, if I let x be 0 and y be 0, then I'm going to get 0 plus 0, which is going to give me a profit of 0. And so that makes sense, because if we're producing something, maybe it's shirts and hats or pens and pencils or whatever it is, if I don't produce any x's and I don't produce any y's, my profit is going to be 0. I'm not going to make any money. And so that's going to give us the smallest profit. What we would essentially be interested in, if P really does represent profit in this case, is the maximum value. And so that might happen at point B or C or D. And so let's plug in those points. And this is kind of done for us, but I want you to see how, the process for getting the maximum profit. If I go with point B, which is this coordinate here in my feasible region, x is 2 and y is 0. So if I plug a 2 in for x and a 0 in for y, and I evaluate what that's equal to, I'm going to have a profit of 6. Now it might be $6 if that really is profit. If I test the next point, which is point C, that means I'm making 4 of x's and 3 of y's. I'm plugging in 4 for x and 3 for y. 3 times 4 is 12, 2 times 3 is 6, and if I add those together I get 18. So that would give me a profit of 18. That's better than a profit of 6. It's definitely better than a profit of 0. Then I would test my last point, where I wouldn't plug in any x's, and I would plug in 7 of whatever the y represents. And that would give me 3 times 0 is 0, 2 times 7 is 14. That would give me a profit of 14. And so we can see we were asked to find the maximum and the minimum. The maximum value for P, and I'm assuming that it's profit, the maximum value is 18. The minimum value within our feasible region is 0. It's 18 if I use the point C, because that would give me a profit of 18. And if I use the point A, that would give me a profit of 0. And essentially that's what we're looking for. We're trying to answer a question by going through this process where we graph our constraints, come up with a feasible region, use our feasible region to get the vertices, plug in our vertices to an objective function, and then either get our maximum or our minimum value. Let's take a look at how this would work in a second example. So here we have what we're trying to do is come up with a maximum profit, and we're going to be selling mixed nuts and roasted peanuts. And you can order no more than 500 cans and packages. And we don't want to spend more than $600, but we want to come up with our maximum profit. Maybe we're doing a fundraiser and we're selling mixed nuts and roasted peanuts in our fundraiser. And so first thing that we would do is analyze the situation. What could we order with our constraints? And again, we can only order 500 cans or packages. We can only spend $600. And so our constraints are going to look something like this. So from the information that's in this picture here, each case of mixed nuts comes 12 cans. And so if X represents our mixed nuts, then each case that I buy, I get 12 cans. However, each case of the roasted peanuts that I order, I get 20 packages. And so I get 20 packages for each Y case. Remember, Y represents the roasted peanuts. 12 cans for each X case, 20 cans for each Y case, but I can't get any more than 500. That's the most I can make, or the most I can order. So there's one constraint. The other constraint is that I can only spend $600. So each case of mixed nuts that I buy costs me $24. And each case of the roasted peanuts that I buy is going to cost me $15. So it's $24 for each X case, $15 for each Y case. That gives me, and I can only spend $600 at the most. So that has to be less than or equal to 600. Also, my feasible region, it's impossible to buy negative cases of mixed nuts. That has to be greater than or equal to 0. It's impossible to buy negative cases of roasted peanuts. That has to be greater than or equal to 0. So these are our constraints. Now, what they've done here is they've gone and they simplified things a little bit. You can divide the first equation by 4 and make the numbers a little bit easier to work with. You can multiply or divide the second equation by, looks like 3, and get 8 and 5 and 200. Graph would be the same, values would be the same. It's the same equation, it's just a little bit simpler numbers to work with. And here is our objective. Our objective here is to maximize our profit. So we would have to come up with an equation for profit. And it says that you make $18 profit per case for mixed nuts and $15 profit for each case of roasted peanuts that you buy and then sell. And so here's our objective function. So step 1 would be to graph our constraints. And if I graph our 4 constraints here, these 4 graphs are what I would get. It looks like there's 2 here. The first 2 graphs are these 2 lines here and here. But then I have x is greater than or equal to 0 and y is greater than or equal to 0, which essentially means I'm in the first quadrant. Once I get those that feasible region, which is this area here, then I want to find the vertices. That's step 2. And so I have point A, I have point B, point C, and point D. And once I figure out what those vertices are, I label them, like B is at the point 25, 0, C is at the point 15, 16, and D is at the point 0, 25. If you have a hard time figuring out what a point is, well, that's the intersection of 2 lines. And so you can take like these 2 equations and use substitution or elimination to figure out where they intersect or what the solution to that system would be. Once I get those vertices, then I'm going to plug those vertices back into my objective function to maximize my profit. And so that's what we have here. Our objective function is that it's $18 for each X and $15 for each Y. And if I plug each of those points in for X and Y and evaluate what the profit is, we can see that my maximum profit is going to be $510. And it would be $510 if I ordered 15 cases of the mixed nuts and 16 cases of the roasted peanuts. That's what linear programming is all about. For tonight's homework, you're really not going to be coming up with the constraints. You're not going to be coming up with the objective function. That's going to be given to you. You're essentially going to be doing steps 1, 2, and 3, where you might already have a feasible region, or you might be graphing the constraints to come up with your feasible region, then gathering your vertice points, and then using your vertice points to either maximize or minimize a function. 6 problems tonight, so good luck on that. We'll see you tomorrow in class.